So, let us look at abstracts, both functional and procedural abstracts, and today I will try to define the meanings of abstracts. The age old and fundamental question still remains, which we will only partly answer today, and that is, so what is in a name? Well, an abstract, and we still have not answered the question what really is an abstract, right. So, today we will answer it, and I know a lot of people who read Agatha Christie books and who, after the initial chapter when the murder is committed, they go to the last chapter where the murder is solved and then they start reading the rest of the book. So, let us do the same thing. So, we have done the initial chapter of this chilling suspense. So, now there is this chilling suspense. So, the next question is, who did it? In our case it is rather who done it. In our case it is what is in an abstract, what is an abstract. And amazingly the answer is that it is an applied lambda abstraction. Well, applied or pure depends on the rest of the application, and we will define the notion of a closure and we will try to define the meaning of abstracts. So, any abstract, especially parameterized ones, are really going to be just lambda abstractions. Yeah. And so, the distinction between an abstract and abstraction is then becomes negligible. Yeah. So, let us go about it. So, what we will do is something that we have not done is that we will consider, since in a functional setting these things are always easier to define. So, we will look at the semantics of ML like functions, right. So, let us look at functions. In whatever we did, we only considered mostly values, and I will make the assumption that it suffices to consider unary functions, and I mean there is a viewpoint in which every function is a unary function, not obtained by Curry. Okay. It is just that any n-ary function can be regarded as a unary function applied to an n-tuple, construction. So, in that sense, in fact, in that sense the conventional mathematical notation for a function is also really that. This is really f as a unary function applied to an n-tuple, right. So, we do not lose too much by considering all functions to be essentially unary functions. So, there is an important aspect of an n-tuple construction before you actually apply the function, but even otherwise, whether curried or not curried, we can think of all functions as being unary, right. So, and so then what happens is, with this it also makes it more convenient and less messy to talk about functions, their parameters and so on, right. So, let us look at the syntax of functions. Of course, now that we have done something about type checking, what I will do is I will define the syntax. So, essentially there are just two constructs we have to worry about. One is function declarations. So, f is a function symbol with a parameter x of type tau naught, and E is an expression of type tau 1, and if you remove this type information, then essentially it is like an ML declaration of a function, right. And of course, even in ML, if the type inferencing has to succeed always, you might have to put at least some type information somewhere in order to make sure that these operations inside E are meaningful, right. So, we will assume that we have fully typed information, right. And then of course, the function call is just f applied to some expression E, right. I mean, so this is a sort of ML syntax. So, we will consider mainly non recursive functions. The extension to recursive functions is quite simple if you clean up the syntax a bit. Okay. So, then as with all declarations and expressions, we have to look at what are the free variables of a declaration. So, the free variables of a declaration are just all the free variables of E, except of course, x, which is a parameter of f, right. So, so in the if it is non recursive, then that is really what it is. If it is recursive, what it means is that you will have to use some form of disambiguation to make sure that f is not included in the free variables of E. I mean, remember that functions are also values, and I mean there is a great unity operating all that. So, if E is if you have some way of recognizing that it is a recursive definition, then what it means is that you will have to remove f also from the free variables of E. Okay. There are many languages which actually, in the case of ML, what happens is the question of whether f is whether if f occurs in E, the question of whether it is recursive or that f actually refers to some previous declaration of f is resolved in ML by a very simple mechanism. It takes the innermost reference and decides on that, right. So, if the name of so it looks through this, and if there is an f here, then it assumes that it must be a recursive definition. Okay. So, so ML has a very simplistic view of that. So, in which case in actual ML programs, this distinction between non recursive and recursive is not very syntactic, it is rather implied rather than being direct. But many languages like Camel, for example, which is really a variant of ML, explicitly requires that if you intend a function to be recursive, then you should put a reserved word called rec in front of the definition of the function, right. So, for example, so if you have a definition like this, so if you have a definition like this, f of x equals, if x equals 0, then 0, else f of x plus 1, f of x minus 1 plus 1, let us say. So, if you have a definition like this, in the case of ML, it automatically takes this to be a recursive function. Okay. On the other hand, this might be part of an ML session in which you may have previously declared this. So, you would actually have something like this. You may have previously declared f to be of type x plus 1. Okay. So, now what ML does is it just basically disregards this, okay, and all occurrences of f here refer to this most recent occurrence, most recent syntactic occurrence in the as part of the interpretation. However, Camel, which is very much like ML and has a very similar syntax and is based on the same kind of principles, type system, type inferencing and so on, actually specifies that you should, if you do not include a reserved word rec here, okay, So, this rec is a reserved word which is supposed to indicate that a function is recursive. So, then if you actually include this reserved word rec here, then and only then camel will take this f to be a recursive call to the same function. If this rec were not there, then what would happen is camel would be looking in the environment for a previous declaration of f and would use that as the meaning of this f. Okay. In some sense, in ML things are very implicit, even though the designers of ML were among the first to point out that there is an ambiguity in programming languages in which you do not use, which most programming languages do not use this reserved word called rec or some kind of a syntactic tag which makes it clear whether the function or a procedure is recursive. In spite of that, they actually have this sort of implicit binding mechanism which binds this f to this, whereas in camel it actually has to be made explicit by means of this reserved word rec. Yeah. So, however, I mean, so in that sense camel is somewhat more explicit and perhaps better so, because we do not know really what kinds of ambiguities the lack of this recursive keyword can create. I mean, we already know how it can create problems in, for example, Pascal functions, right. So, anyway, so we'll for the present assume that it's these are non-recursive things. If the only difference in our semantics if it becomes recursive is that what it means is that you have to have a y combinator, some form of recursion combinator, just like we found for while loops, right. That's going to be all the difference. Otherwise, the difference between recursive and non-recursive is really a question of identifying what are the free variables and what are the defined variables.
So if E is non-recursive, then is f a free variable of E?
If f occurs in E,
Yeah.
yes.
So but why should it be, since x is also being declared at the same place as f is?
No, the syntactic ambiguity that I was talking about, if you claim E is not, so let's be explicit. Let's take camel like syntax, where if you intend it to be recursive, then you give this keyword rec, otherwise you do not give the keyword rec. So, if you do not give this keyword rec here, okay, then what it means is that the elaboration of this expression means that your environment, the environment in which this expression is going to be evaluated, should already have some definition for f. If it does not have a definition for f, what a camel interpreter will do is it will say that f is an undefined variable. Okay. This is the non-recursive case. In the recursive case, this reserved word rec will actually help it to identify that, therefore, within the scope of this definition, all occurrences of f are the same as this occurrence of f, and since f is a defined variable here, it is not a free variable. Okay. All this is not explicit in ML, it is implicit.
Excuse me, so is it necessary to have the type of x same in both the functions?
In these two?
Yes, sir.
No, not at all, not necessary.
So, but if we do not give this rec, so then this f of x minus 1 will be bound to the first function.
Yes, it will be bound to the first function, and if the types of the x here and the x here are different, then you are going to get a type error.
So it means it should be then. So if you are not.
So if you do not intend it to be recursive and you actually intend this f to refer to something that is already available in the environment, then the type checking problem has to be satisfactorily addressed. that is all, right. Right. So, otherwise, so in the case of free variables, so essentially all the variables in E except x are free. Okay. If I include this explicit rec here, then the free variables of this declaration are, so essentially the way I am looking at it now is that the free variables of rec f x of type tau naught, the whole function of type tau 1 equals E is equal to all the free variables of E minus x and f, okay. And the free variables of, if f were not recursive, then any occurrence of f in E refers to some previous binding. So, that f is a free variable of E, okay. It is as simple as that, right. The defined variables, so of course, so what it means is that if you did not have the keyword rec or the reserved word rec, then f could be both a free variable and a defined variable of this definition. So, the defined variable of this definition is just the symbol f. And so this is as far as definitions are concerned, and in the case of a function call, the free variables of a call to f with an actual parameter which is an expression E is just f union the free variables of E, right. Right. So, so let us just go through this. So, firstly of course, we have to look at the static semantics of these definitions. So, let us look at the static semantics of functions. Now, our type environment, as usual, a type environment over a set of variables or a set of identifiers is just some identifier to type binding, okay. So, now the types here, previously the types we had were just base types like integer and bool and so on and so forth. But of course, after having spent so much of time on the type lambda calculus, it is clear that now our types actually expand out. In addition to the base types, you have all the type constructions that are possible, well, either in the simply typed lambda calculus depending on what your language is, or the polymorphic lambda calculus depending on what your language is, right. So, I am leaving this unspecified, but essentially it includes something more than just the base types. It includes all kinds of functions that you can create on base types, and if you are considering a polymorphic case, it also includes all type variables and type constructors, including the for all quantifier on type variables, right. So, whatever can be defined from the base types using the language of the using the type language of the polymorphic lambda calculus is included in this. And of course, since our functional language is an applied language, is an applied lambda calculus, essentially all the types of the underlying application and so on, and the higher types created by lambda abstractions on those applications, all of them are included in these types. Okay, so that is how you get higher order functions from a simple application, right. So, without much ado, let us just go through the type definitions. So, if E is of type tau 1 and then this definition of this function f with x as a parameter tau of type tau naught is that so the type checking rule is just this, that you should make sure that the body of the definition is of the same type tau 1 as is given in the declaration. And then what does, and this definition creates a little type environment which associates with f the type tau naught arrow tau 1, right. So, it takes that, so essentially the function takes an argument of type tau naught and gives you a result of type tau 1, whatever tau naught and tau 1 might be. They might be polymorphic types, they might be monotypes, they might just be base types, whatever is representable, right. And then in the case of a function call, of course, the type checking is that if this expression E, the argument should, if it is, so if your static type environment gives you the type information, gives you the type of f as being something of the form tau naught arrow tau 1, then this function call type checks only provided the argument to the function call is of type tau naught, right. So, if the argument to the function call is of type tau naught, then this function call is of type tau 1 and it type checks. So, essentially that is the type checking for function calls. You just have to evaluate the type of the argument. Remember that all this is done at translation time, it has got nothing to do with executions, it is all done at translation time. So, essentially you look at the expression from the static environment that you have already created when you are looking at this expression, you evaluate the type of this expression, and if this expression has a type tau naught and your environment, assuming a declaration before use strategy, your environment already has created for f the binding, the type binding tau naught arrow tau 1, then this type checks, this function called type checks, otherwise it does not, right.
Why have you written that as a side condition?
Why have I written that as a side condition? Oh, the side conditions are usually of this form, that in the main premises and the hypothesis we only use what is directly relevant to the syntax of that phrase. Side conditions are all the information that could somehow be gathered or have been earlier gathered in through some definitions or some declarations or through applications of other rules, right. So, this is given the type environment gamma as an assumption, this is a piece of information that is inside gamma and is not part of the current syntactic phrase of our rules. So, the current syntactic phrase is just f applied to E, which has one sub expression E. So, the premise has to be in terms of just that E, right. So, given this assumption gamma, if you can prove, this is the provability symbol, that E has type tau naught, E green, remember my coding, green is part of the programming language, blue is something else, some other pieces of information, derivations, inferred information and so on and so forth. So, if you have inferred that this E, given this type context gamma, if you have inferred that this expression E is of type tau naught, then you can infer that this call f of E1 is of type tau 1, provided inside this gamma you have this binding for f that it is of type tau naught arrow tau 1. That's how all our rules have been going. That's how site conditions are given. The premises and the hypothesis, the premises and the conclusion of any rule are just the syntactic sub expressions, consist of just the syntactic sub expressions of the phrase that is under consideration. Yeah, right. So let us look at the dynamic semantics. Of course, in a dynamic semantics, what we often do is we transform the syntactic phrase. It is part of the symbol manipulation of the runtime, right. So in the dynamic semantics, we have the notion of a runtime environment, rho, right, which of course is a binding from identifiers to values, and now values take on a new meaning. Values are not just values in the base types of your language, values include also values of higher types constructed through various functions. Okay. So, this values is now a loaded word. I mean, it is loaded with, as I said, functions are also values, functions of functions are also values, and all higher order functions are values, right. So, and of course, looking at it the other way from the lambda calculus, everything is of course a function, whether it is a value or a function, right. So, this values includes all these values of higher types that you might have, starting from the construction of your base types, right. Okay. And then, so if you look at values, originally we had just this. If you go back to some of the age old semantics that we gave, we had only the natural numbers. But of course, we showed how you could construct other structured constants from this, and we also include what are called closures. Okay. And closures are just, so this other structured constants could be records, tuples, lists, etc. This base values could be something other than int 2. I mean, you could have int and bool and real and character and so on and so forth, but in addition we will have this thing called closures. Okay. And we will look at a closure, and a closure is really nothing more than a lambda abstraction, right. So, right. So, so let us look at this. So, let us look at the semantics now. So, given a runtime environment rho over a collection of identifiers V and a type environment V, because you might also have to do runtime type checking in certain cases. So, we will always look at, now we will look at the semantics in terms of both a runtime environment and a static environment or a context gamma, and both the runtime environment and the context are over the same set of variables, right. So, whatever, so a basic constraint which has to be satisfied by these two environments is this, that the runtime environment should somehow be type consistent with the static environment. So, unfortunately, there is a plethora of colons here, and colons is a very highly overloaded operator in whatever I am doing. This colon here is a new symbol, okay, which essentially says that the runtime environment over V type checks the is type checked by the context gamma over V, provided this colon of course is a colon that I always use when I write a logical predicate with quantifiers. I mean, it's something that separates the variables inside a quantifier, bound to a quantifier. This colon is the colon of the type, right. So, what we are saying here is this: the runtime environment is type checked by the type environment gamma, provided every variable in the runtime environment has a value, right? Every variable in the runtime environment has a value which is given by rho v applied to that variable, right? And that value should have the same type that gamma gives it, right? Right. So, this is the constraint that we are working, we are going to always work under. I mean, this ensures that things also runtime type check if necessary. So, this new colon is really an extension of this old colon. This colon, this light blue, so these two this dark blue colons are really essentially the same. This colon is over particular variables or values, this colon is over collections of variables or values. I mean, it is just an extension from single variables or values to collections of variables and values. So, these two dark blue colons, the left one is actually an extension of the right one. This light blue colon of course is just part of this my symbolism for writing predicates, that is all. I mean, there is nothing more to it. Yeah. So, this is the basic constraint under which we can define the semantics. And so let us look at function definitions. So, function definitions. So, what happens at execution time? You have, I am assuming I have removed this capital V as a subscript, given a runtime environment rho implicitly over some collection of identifiers, say let us say capital V, such that it type checks with a type environment gamma, which is again over the same set of identifiers V. This is a function definition which goes, so this is a function declaration, so it creates a new little environment. Okay. So, it creates a new little environment, and what is that new little environment? That new little environment, which is a runtime environment. So, functions have also all identifiers have values, actual values. And what is the value of the function f in this new little environment? It is a lambda abstraction over some expression containing E, okay, such that this huge expression is of type tau 1. So, one constraint of course is that this tau 1 and tau naught are specified here, right. So, now this, what does this huge expression do? Basically you have to evaluate, you will have to give E has, what are the kinds of variables that are there in E? E could have bound variables, namely x, since we are considering only unary functions, E could have the x as a bound variable. E could be an ML like expression, so it could have let and local and so on and so forth, and more declarations in it, which all are bound variables. Okay. If it is, and since let us assume for simplicity now that E is non-recursive, so it has no occurrence of f. Okay. Then what are the other identifiers that could be there in E? Those are all the non-local references. So, E has to be evaluated assuming that all those non-local references have values given currently by the environment rho. Okay. So, now I want to look at this function declaration in isolation. Okay. So, what do I do? I am saying that this function has a value which is given by a lambda x, which is the bound, which is the argument of this function. So, essentially parameters are going to be bound variables in a lambda abstraction. So, if you have several parameters, then there are going to be that many lambda abstractions, either in a single lambda abstraction over a tuple or that many curried lambda abstractions. You can take your pick, the two things are isomorphic. Okay, but since we are considering unary functions for the present for simplicity, so it is a lambda abstraction over x, and the expression that it has cannot just be E, because E has too many free variables which are essentially non-local references. So, E could have all kinds of bound variables in it. In addition, it could have some non-local references which have values in the current environment given by rho. So, essentially if I want to specify this function declaration in isolation, that means if I want to remove it from its current ML session, this is a function declaration that is part of, let us say, a larger ML program. Now, if I want to take this function declaration out of that ML session and put it, let us say, in a separate ML program as a standalone ML program by itself, then what should I do? I should then in the current ML session extract the values of all the free identifiers that occur in E, assign them the same values, and then I am ready to take this definition out and look at it in isolation. And this is what that does. Extract for all the free identifiers in E, extract their values as given in the current environment, right, and create fresh let declarations which give you those values in the current environment. So, essentially what I am saying is, if I have an ML session, a simple ML session in which I first defined, let us say, val y equals 3, and then now I define a function f x, let us say, of type integer, and let us say this is also of type integer, let me be completely explicit, and this is equal to just x plus y. Okay, I am not, for simplicity I am not considering any non-local references. Then what I am saying is, what is the meaning of this function? This function has a meaning in this current environment. And what is the meaning of this function? The meaning of this function is the same as replacing this by a new lambda abstraction, okay, x of type int, such that let, the only non-local reference here is y, let y equal 3 in x plus y. So, essentially that is what I am doing, right. It is a closure because now there are going to be no free variables in this lambda abstraction. The lambda abstraction that you now get is a completely closed lambda expression with no free variables. Right. So, that is why it is called a closure. The reason we have to look at all abstractions as closures is precisely, it also has a pragmatic basis, and that is that when you look at a function or a procedure as an abstraction, then what you are trying to say is that it is something that stands by itself. I mean, I can take that function from you for that for the same purpose for which you defined that abstraction, for a similar computation, and I can call that, which means I can pull it out of your program or from a library of programs and use it somehow. The only problem that is created is when there are non-local references. Okay. And how do I resolve those non-local references? If you had non-local references in your function, I extract all the values that are expected at that time and use them, only then I am guaranteed that it will work right, and that is essentially what I am doing by this closure. Right. So an abstraction is really that, I mean it is an abstract is really an abstraction in that sense, right. So and that is in fact the purpose of an abstraction too. I mean it is something that should stand out in isolation. Unfortunately, we have a lot of environmental variables and so on and so forth which prevent us from taking it directly. So, in order to give an abstraction a meaning in isolation, you have to also include the information that of whatever is relevant from the environment that should go into the meaning of the abstraction, and that is really all that we are doing. Yeah. So, let us look at function calls. So, that is a function definition. So, then as a closure, a function definition then stands out by itself as a lambda abstraction. And what is a function call? Well, a function call is just this. A function call, if a function definition is a lambda abstraction, then a function call is just an application for that lambda abstraction. So, it is a beta reduction. Okay. And of course, in an ML like language, in an ML like language we do not directly have beta reduction, but we have beta reductions in another form, that is in the form of lets. So, this let, if you look at let carefully, it is really like an application. If you remember, if you look at the semantics of let, what we gave as a semantics was that you create a new little environment where this x has this value, and then in that environment you evaluate E, which means that all free occurrences of x in E will take that value from the new little environment that is created. Okay. But that is another way of saying forget about this x, replace x completely by the expression that it denotes and keep the environment the same, do not create a new little environment. So, our semantics of let could have been alternately written out as a pure form of beta reduction with no notion of an environment. Okay. Unfortunately, in imperative languages, I mean, so in a purely functional language we could actually do that. Every variable can be replaced by its body and often out of context. But in an imperative language, because of the possibility of side effects and because of the fact that there is a huge amount of environment that really needs to be maintained, it is necessary to keep that environment information somehow. But otherwise, the pure ML like language that we are defining, we could have defined without an environment by just using the notion of a substitution, which makes a let construct in ML just a beta reduction. A let construct in ML is just a beta redex. So, let x equals E naught in E is just lambda x E applied to E naught. Okay. So, this let actually is just like an applied lambda abstraction. Assume that there are no local references in E, okay. Then this would just be this, and we would not require any environments, we could actually do syntactic replacements, but we require environments because there are redeclarations of variables and so on and so forth. So, we used it, it is more convenient. So, but essentially a let construct is just a lambda, is just a beta reduction, is just a beta redex, and so a function call is just a beta reduction. Since a function is just a lambda abstraction, a function applied to some argument is just the lambda abstraction applied to that argument, it is just a beta reduction, right. So, the kind of mechanism that we have been looking at so far really is what is known as call by value. Okay. So, essentially what we are doing in call by value, I am redoing that function call. I can rewrite that function call more explicitly in this fashion, so that it models our further discussion on parameter passing. So, you got the function is called with an expression E naught, then you evaluate E naught in the expression language. So, essentially you do not touch the function till you have evaluated E naught completely, and E naught has finally got reduced to some value m. Now, here again this m could be could be any higher order value, okay. It could be a function value or whatever, it could be anything, okay. But I am using m in order to keep it uniform with whatever we have done before as something as a value, as a hard value that is somehow available. Then the application of f over E naught is just the application of f on m, which means that it is just this let construct, where f is of course just this lambda abstraction, where and of course I have to here again I have to worry about those non-local references and so on and so forth, right. So, there is a let inside let, if you like, whatever, and having done that it is just this, yeah. So, this do not take this E totally very seriously. This E might have non-local references, which means again you will have to write a let row, again you will have to write this kind of an expression, okay. So, maybe I will just give it a different name, I will just give it the name E1, where E1 equals let row over the freeway over the non-local references of E in what? E. Yeah, right, where of course the function definition is of the form f of x colon tau naught equals E, right. So, then this is what, so here what are you doing in call by value? You are evaluating the argument completely, and function call is applied only after you have got a perfect value. So, if the evaluation of this argument is an infinite computation, what it means is that you can never return from this function call, which is something we have all experienced. So, that brings us essentially to what is known as to various parameter transmission mechanisms, their application in the lambda calculus and functional languages, and also in other imperative languages. So, let me just quickly go through what happens in the lambda calculus. In the lambda calculus you have two mechanisms, one is called the call by name. These are the two principal mechanisms which have applications also in other programming languages. So, if I take, and what happens in the lambda calculus actually also happens in other programming languages to some extent. So, if you remember, we considered this infinite computation. We said that because of replicating operators in the untyped lambda calculus, you can get infinite computations, even though by taking a different reduction route you could get a normal form, okay. Now, there is a theorem in the lambda calculus, in the untyped lambda calculus, that if you take the leftmost outermost beta redex always and reduce it, and you having reduced that, you will get a new lambda expression, again choose the leftmost outermost beta redex. That means do not go deep inside to choose the redex, look at the outermost levels of parenthesis to find a redex from left to right, read from left to right and do this. If you do a leftmost outermost reduction always, which is deterministic, okay, remember that the lambda calculus operational semantics is non deterministic. But now if I make it deterministic, by choosing always the leftmost outermost beta redex to be reduced. Then there is a theorem in the lambda calculus, which I am not going to do, is that if there is a normal form, beta normal form, then this order of reduction is guaranteed to produce it. Okay? And this is clearly a case of a leftmost outermost beta reduction, and this is called call by name. Okay? Whereas if you have a call by value, then you evaluate an operand completely and try to reduce it completely before actually doing a beta redex. So, you go deep inside. So, essentially while you are reading the lambda expression, you look at all the operands of beta redexes and try to reduce them. An operand of a beta redex could itself contain beta redexes inside. So, which means you go inside and try to reduce the operands within there, and so on and so forth. So, you are actually going inwards, but you are not going too deep in the sense that you are not going deep inside the lambda abstractions. You are going only deep inside the operands in an attempt to first reduce the operands to their normal forms and then apply the beta reduction. So, you will always, given an application of this form, you will not go deep into L, you will go deep into M. You will want to reduce M. In order to reduce M, you find out whether there are any beta redexes in it, and in which case you take their operands and reduce them, and so on and so try to reduce them, and so on and so forth, right. So, you always look at the you always look at the operand of an application and try to reduce it first. Okay. That is really what we did in call by value. Given an application, you take the operand and try to reduce it first and then do the application. Unfortunately, in the untyped lambda calculus, this can give you an infinite computation. So, it is not guaranteed to produce normal forms even if they exist. Yeah?
Sir, if this is the problem, why at all do we use call by value?
Yeah, because call by value can converge faster, right. So, once you have type lambda calculi, there are no infinite computations, normal forms are guaranteed. So, now call by name and call by value should both yield the same results, but in a type lambda calculus, that is a polymorphic type, you can have operators which are replicating. Okay. So, if you have a replicating operator L applied to an operand M, then a call by name can produce copies, lots of copies of M, which means that you will have to reduce each of those copies of M individually separately later. On the other hand, if you decide to reduce M first itself, and then you do the application, even if L is a replicating operator, you will still have a normal form without doing extra reductions on copies of M. Okay. So, it is also the easiest thing to implement a call by value reduction, and it converges faster, especially in the presence of replicating operators. So, that is why an untyped lambda calculus is completely of no use to man or beast, because its semantics requires that you have to always use a call by name implementation if you want to get normal forms. So, therefore, most functional languages use call by value, right. So, we will start parameter parsing in this context next time, and we will look at other parameter mechanisms in imperative languages.